Hi, welcome to another session on advanced algorithms. We stopped last time in the middle of discussing our first really usable three-set algorithm. I didn't really show the algorithm yet, but we were discussing a warm-up exercise for two-set, which is, as you know, a much simpler problem. And the algorithm, it looks a bit scary, but actually it's a very simple idea. You pick a random assignment and just locally adjust it so that one of the clauses that are currently not fulfilled becomes satisfied, and just keep on doing so until you find a satisfying assignment, or until your number of tries ran up, and then you conclude that probably there is no satisfying assignment. And this kind of simple strategy already gave you a kind of usable algorithm for two-set, so you could control with this parameter what the error probability is. And the analysis was basically relying on this Markov chain. Maybe this picture is more memorable. Just revoke your memories again revive your memories again, not revoke, because we will need a similar analysis for the three-set algorithm. So in particular, we had this notion: if there is a satisfying assignment, we don't know what it is, but if there is one, we can determine for any given assignment that your algorithm currently stores, you can determine what's the number of variables that are assigned the same way. So you can use these xi as states. And then when every local adjustment step means you move from one I to an adjacent one, either up or down. And you could bound the probability for this two-set case so that you go up with at least probability 1/2. And we took a step back and analyzed these kinds of Markov chains where the probabilities are exactly given like this. And we saw that these give rise to difference equations, kind of a discrete analog of differential equations. And with similar tricks, and in that case it was easier to determine the derivative, if you like, the differences explicitly, and then compute from the differences, the actual function that we're interested in. So in the end we found that if we start at 0, so that's the worst case for the random assignment where it could land, so it has the maximal, just assigns everything the opposite way than the satisfying assignment we're looking for. Then the expected number of steps till you reach this sink, the state k, where the algorithm terminates, is k squared. So if you double this number and wait for so long, then you have at least 1/2 a probability to succeed. That was Markov's inequality. And the trick was that we take these certainty times 2k squared runs as certainty times repetitions of independent runs. And then we get this nice probability bound. Now, two-set is kind of boring. We would like to do three-set. So let's try our good algorithm and just apply it to three-set. And well, probably or hopefully you guess that we will not come up with something like k squared or so for the expected runtime, because that would mean we find a polynomial time randomized algorithm for a three-set. That would be a bit surprising, right? Because we actually believe that randomization is not extending the class of polytime solvable problems. But exponential is not exponential. It might be something with a good small base, like in the FPT world. And so it's interesting and not totally clear upfront what the result might be in this case. To make the story short, the very same idea goes through, you can just pick one of the clauses that's currently not satisfied, choose one of the 3 literals uniformly at random, and flip it. Then you get a new assignment. And you always make a step in the Markov chain up or down. But the probabilities are a bit different, of course, because we now have 3 literals per clause. And what you can show is essentially you go up with probability at least 1/3 and down at most with 2/3. By the same argument, at least one of the variables must differ from your current assignment and the satisfying one. But that's about it. I mean, in the worst case, there's exactly 1 literal that you have to hit to make progress in the positive direction. And what that means, so this was our P, the probability to go up. Remember, in the general setting, we even allowed this to depend on I, which we actually never gonna use in this course, but just in case. And then we had this solution for yi star. Why not just copy it? That was the most general setting. Okay, why not copy it? Because it's fiddly. Make it blue. Okay, just put it somewhere down here. Oh no, made a mistake. I'm still practicing with this kind of stuff. So the point is that the A's were Q over P, and the B was minus C over P, and C was always 1 in our case. And then a lot simplifies again. The -1, that's also the same. That was the generalization I didn't do. And this is just 2 to the I. And then we have the B is -3, because P is 1/3. For the analysis, as last time, just to remind you, we dropped the greater equal and lesser equal. We just took as a lower bound the Markov chain where these are exactly 1/3 and 2/3, or 1/2 and 1/2 last time. So that's the B, and then we have the sum j1 up to I, and that's 2 to the I minus j. And if you sum in reverse and simplify, then this is just the sum of the first powers of 2, and these have the particularly nice property to sum up to 1 less than the next power of 2. Okay. That's 4 times 2 to the I and plus 3. That's the white dot, which doesn't tell you so much. But you might also remember from the slide above that we just have to sum the negative of all these white dots. You integrate if you have the derivative to get the real function. All in by the same summation formula. What you get is this. And that's the expected number of steps you need in the worst case till you run into the sink, till you find the satisfying assignment. So in effect, we need 2 yi runs to have a guaranteed probability of 1/2 to succeed. That's the same Markov trick, Markov inequality trick we've used 10 times last time, which would be like 8 times 2 to the k runs or iterations. which is quite a number, right? In deterministic time 2 to the k, we can just guess all assignments and check the formula with an additional factor of n. So this is actually worse than the brute force method. Okay, it's not so great. So this is what sometimes happens with randomized algorithms. You do your best and design a very cool method, and then it's just awfully slow, or succeeds with an awfully small probability. We'll actually see another example of this, I guess, later this time. And then you can either screw everything or think about what might have gone wrong. Of course, we would like to do the latter. And the problem is that this Markov chain here with the 1/3 and 2/3 has a strong drift to the left. If you keep that running, it will basically get stuck at the state 0 most of the time. And it's quite unlikely that you will ever get far away to the right. Yes?
Isn't it likely that with a good heuristic, you might be able to fix it to a certain degree? I mean,
so you're suggesting to use some heuristic to do what?
Well, the probabilities are bigger than 1/3 and smaller than 2/3, and with a good heuristic, could theoretically be possible that it would be 1/3 to go to the left and 2/3 to go to the right. I mean, it's...
Okay, so you were suggesting instead of just picking a literal uniform, you could do something more clever. I mean, you can certainly try, but I guess in the worst case, you might... It's hard to make sure you don't do worse in all cases. Yeah, I think it's in that case there's not a simple trick to get rid of this problem. The point is, if this Markov chain is run for a long time and tends to end in this 0 state or close to it in any case, there's no use in running it for a long time. That's basically what we did. We just analyzed, let it run the same Markov chain and hope that it at some point by chance hits this state k. And the answer is, okay, it will, but you will have to wait a long time. So maybe it's better to hope for a good starting point in the chain than to keep it running for a longer time. And that's what we're going to do. The point is, you could also just keep on guessing assignments. That's the other extreme. Guess an assignment, check whether it's satisfying, and if not, do it again. That's also no better than the brute force method, because an expectation, in the worst case, there's only one satisfying one, and you have to wait 2 to the k iterations till you hit that one, right? So these are the two extremes, and we would like to go somewhere in between. And that's Schöning's randomized 3-set algorithm. There's a few interesting numbers that I hope make you look forward to the analysis. So let's fix the notation k is the number of variables as before. And we choose, essentially choose random assignments and do, so there's two magic numbers. One looks scary and one looks harmless, but they're actually both important. So we keep on doing the local search only for 3k rounds. And if we didn't run into the sink after 3k local steps, then we just throw away that assignment and try one more time. And this is, of course, the huge number. So you only do a little bit of local searching and do a lot of repetition. And the rest is essentially copy-pasted from above. We have the 3 literals. That's what I just sketched but didn't write down. You have the 3 literals instead of the 2. You pick one of those at random and change the assignment by negating one of those. The statement that we get for this algorithm is basically the same as above. We also have this parameter certainty, with exactly the same meaning. And we get a runtime bound, but this is actually trivial because it's just the 4 loops. So you add a factor k to this for the inner loop, you add a factor n for checking assignments, and the rest is just, well, first semester analysis of algorithms. The interesting part will be to prove number 2. So let's make a check mark here. So as before, we will assume this is satisfiable. So there is at least one satisfying assignment. And of course, we use the same analysis with this Markov chain as before. So the same model, but this time it will not help to bound the expected number of steps till you run to this accepting state, because we know that we are aborting that local search pretty early on. So we will have to do a different kind of probability trick. So what we need is some lower bound for the success probability. Of one such local search round. And this takes a random starting state in the Markov chain. And well, the meaning of this number I was just the number of matching variables. So if you keep this alpha star fixed, then I is just a binomial distribution, where for each variable you have probability 1/2 to pick the right assignment or the wrong one. So we can already note for reference the probability to start in this state I is k choose I, and because the probability is 1/2 in both cases, it's just 1/2 to the k. So let's draw this chain slightly differently. I usually drew it horizontally. Let's draw it vertically, and look at over time how such a walk in this Markov chain looks like. We can go up, we can go down, 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 and then at some point in time we might get absorbed in that state k, and then the run is finished. If we're in this state I, then we need k minus I, and I'll call this u up steps to reach the state k, which was the absorbing one. And then the length of any such path always has to have this component u, and some number of steps that we go up and down. So what we would like this qi to be is the probability to reach the absorbing state. And in this less than 3k steps that we give the algorithm. So if u plus 2l should be less than 3k, certainly l must be less than k. And what we'll actually use is we'll consider the case that L is exactly U, simply because it suffices to get the bound that we need, and it makes the computations a bit nicer. I think other than that, there's not a very compelling reason to use exactly and only this value. So we'd like to get a lower bound on this, and the probability to reach that state in at most 3k steps is if we first condition that we will only look at paths of the length where L is U, so paths of length 3 times U. It seems like a rough lower bound because there's many more different lengths of the path that are possible, but for a lower bound it's certainly a usable lower bound. And that's, well, if we know that we use 3U steps, then exactly 2U of the 3U steps must go up. And that's the point where this is nicer to compute. You have 3U choose U different ways to select the steps that go down. And these are the probabilities for so many steps up and down. And now we would like to rewrite this, well, to simplify that term, and what essentially will pay off is writing, well, simplifying the binomial coefficient and the factorials. So it's a formula we've used before. This time we need the upper and lower bound. And I'll use this notation here that avoids having to write this ugly term twice. So this should be like an interval. So the interval between 0 and 1, and now we do interval arithmetic. We just multiply both sides with what comes after that. I mean, there's a way to make this rigorous. What exactly that means, you just have to lift the operations, and as long as you do just scalar multiplications and stuff like that, it's kind of harmless. So this is the same as saying n squared is larger than this and smaller than 2 times this. Okay? I will not overly abuse this, but maybe you would like to take that notation and use it. I find it kind of helpful to keep things concise. So we use this for the binomial coefficient. If you write down the factorial representation, we would like to get a lower bound on this Q. That means we use the lower bound on the top and the upper bound in the denominator. That's why the factor 2 here comes up, because it's the upper bound. At least one ugly kind of computation per lecture is mandatory. Now the e's just cancel out because there's 3u up here, u and 2u up down there. Then here we can simplify a bit by canceling a few things, but it doesn't get extremely nice. There's a square root 3 left here. Then an 8 below because we can pull out another factor of 2 from these 2's. Did I make a mistake on my sheet? Okay, we'll see. Well, I'm canceling one of these over here. Then from the u's, what's left is a 1 over square root u. I only find the 4 here. Maybe I screwed up. It doesn't really make any difference for the statement in the end. So the e's are gone, as I said, and what's remaining is 3 to the 3. Well, 1 to the 1, we can exclude that, and 2 squared, and the whole thing to the u. If you like, you can write this as 27 over 4, but because we will use it up here, you can actually leave it like that. So now we insert this here, and what we find is there's some constant, and well, either this should be an 8 or it should be a 4 in my notes. Either way, it's some constant that we're not extremely interested in. And then we can combine these all together. So we have 3 to the 3, another 2 from here, 2 squared, 3, and 3 squared from here, and this whole thing to the u. Looks ugly, but actually most things cancel. So what's left is c divided square root u, u2 to the minus u, or 1/2 to the u.
I didn't get the last step.
Which step was the problem?
Where are these 3 to the 3 times 2 divided by 2 squared times?
So I might, so this was kind of a side calculation, which used Stirling's formula, so this kind of belongs here as well. And then we used that in here, and now this is continuing from above the QI. Okay, yeah, I could have, yeah, it's a bit confusing. Should have had more indentation here. So this this bound is actually assuming that we're not directly lucky and hit the state k. So we might add that qk is actually 1, because the probability to succeed in less than 3k steps, if we already have the satisfying assignment, is 1. We don't do any more steps. Okay.
In the beginning, we said L has to be smaller than k, but
yes,
since u is depending on I, isn't the worst case that I is big and such L can actually be bigger than k?
So you're concerned that this might be violated with the choice that L is u?
No, I mean, if L is u, then what we're doing is right, but the probability that we're calculating isn't complete yet, because we're basically missing the ends where L is smaller than u and where L is bigger than u and actually bigger than k.
So you're right, we're leaving out all the cases where L is not exactly u. And by that we only get a lower bound for this probability qi. So the reasoning is there's many ways, so there's many paths that might take you from I to k. They all have this shape of the length. And of all these paths, there's a certain subset of paths which exactly have length 3 times u, which, as I said before, there's no intrinsic good reason why we just focus on those, except for the point that it makes the calculations a bit nicer. And if you just ignore all others, you only make the probability smaller. In a sense, I see one problem here in that this equal is not quite true because it leaves out the conditioning. So this first half is certainly fine, but this formula assumes that we condition on the event that the path has this length 3u. And there's many other paths. So I think this is, yeah, there's a step here. We should add the probability that the path is really of this length. Otherwise, this is just the conditional probability. Given that the path has the length 3u, then the probability to have so many steps up or down is like this, and everything else follows. Yeah, I think I'll check that again, and we talk about that step next time. I think there must be something missing at this point.
Yeah, I think there's another problem because there are shorter paths and longer paths, and so we shouldn't be able to calculate a shorter or bigger bound on the probability because we are excluding the longer paths where L is bigger than k because I is big.
I think what you have to do is consider all paths of this kind of length. So consider all L's, and then show that you still can bound the resulting probability in this style. But I don't remember that step. Yeah, I suggest we go on for now and talk about that one more time. So this here is to be questioned. Yeah, it's good that we talked about that again. I'm reasonably convinced that this result down here is the right one, even though the path that I showed you is not complete. But let's assume that this is our working hypothesis. Then this was only a bound for the probability for a certain starting state. Okay, we draw a random assignment that takes us to some starting state I, and the probability that one of the outer loop iterations, choosing a random assignment and do the 3k local search steps, the probability that this iteration succeeds must also take the random value of I into account. So we take a Q, and that's the probability of one round to be successful. Well, that's just basically unconditioning. We take the probability to go to a certain step, and then the probability to succeed if we are in that step. Then we split off the case for I equals k. Then we know the probability to hit exactly that assignment must be 1 over 2 to the k. And then for the remaining ones, our qi is of this shape here. And it's convenient to sum over the u's instead of the i's. So recall that the u was just k minus I, right? That was on top the probability to have exactly a certain number that was the probability to start in state I, to have a certain number of matches in the random assignment. And because this is symmetric, it's the same for u and I. And then the probability bound for the q, just have to insert that. Okay, we can pull out a few factors that are constant. And here this u is at most k, so we make the whole thing smaller if we divide by the largest u. Then we have this factor that does not depend on u. And that's it. And then we notice that this can go into the sum. Because this is exactly the summand that's missing here for u equals 0. And then what's left inside of here is this, and we can add a factor of 1 if we would like. Another trick is that this sum is just the binomial theorem. That's nothing else than 1/2 plus 1 to the k. And if you apply it backwards, that's maybe the way you know it. That's the binomial theorem, often a useful step to simplify such sums. And that's of course just 3/2, which we combine with the 1/2 because they're both to the same power. So it's 3 over 4 to the k. Okay, what was that? That's the probability that one of these outer runs terminates with a satisfying assignment. That included drawing a random assignment and doing 3k iterations of this local search. So that was the probability for success, and then by the most famous tricks as before, if we have the probability, then 1 over the probability is the expected number of trials that we need. And we can bound that. Okay, now we can insert our C. And then you recognize that this is the shape of the function of the number of repetitions in the algorithm. And if we multiply by 2, so 2 times this, as always, gives us a probability at least 1/2 to succeed. And okay, if my computation of this constant was fine, then maybe the algorithm is a bit too conservative. But we had a flaw in the analysis, so let's wait till the end. So that's the expected number of trials. So you get with probability 1/2 the right answer. So one-sided error Monte Carlo method. If you leave out this certainty parameter, and if you keep that in, then you're essentially doing certainty independent repetitions of the whole thing. And that's by the same argument as before. Each succeeds with probability 1/2, so that they all fail is 1 minus 2 to the minus certainty. That's the same as before. And so we found that this number is explained exactly because of this success probability. So this algorithm is a nice connection to the first part of the lecture, right? Because it was it's inspired by picking a parameter that makes your algorithm kind of more tractable, because we only count the number of variables here, but still 4/3 to the k is for large instances maybe still not fast enough. But it does not use any of the algorithmic techniques that we considered in the FPT world. It does not do any depth-bounded search tree or so, right? In that case, in that sense, superficially it's related, because it's an algorithm that tries to lower the exponential part, and it does so by randomization, but it doesn't have any other connections to the first part. We have one last example of a randomized algorithm that, like the algorithm we've just seen, uses several independent runs to boost its success probability. But unlike all we've seen up to now, it tries to do that a bit more cleverly. Instead of just throwing everything away and computing the same thing again with new random bits, we try to do something more sophisticated. And the problem that we're considering is the min-cut problem. You might know it in one or the other version. This one is a bit peculiar because of this multi-graph, but you could extend the algorithm probably to a general weighted graph, but it makes the description a bit more obscure. That's why I left it like this. So we are given a graph, and we have essentially weights on the edges, but we think of these as kind of small numbers and integers, which is not a too severe restriction. And if you would like to draw it, then you can just assume that if an edge has weight 5, then you draw 5 parallel edges. That's why I call it a multi-graph here. We're looking for cuts in the graph, which is just a partition of the vertex set into 2 disjoint parts. And we would like to minimize the cost of all edges in the cut, so all edges that cross the cut. So, well, to just do a very small example, you can add a few parallel edges if you like. Okay, what's the min cut in this thing? That's a boring case. Let's add a few more here. What's the min cut? What would you say this year? Something better than 3? So the cut graphically would be like this, and mathematically consists of a subset of the nodes. And so these edges are in the cut. In the drawings, I always assume these edges now are unweighted, because the weight is just counting the multiplicities. Okay, how do you compute minimum cuts? Well, first of all, the problem has a few nice applications, like destroying a certain network, making it unconnected. What's the minimum number of edges you have to destroy? It's kind of been used in World War II for that. The oldest and most well-known algorithms for minimum cuts are based on max flow algorithms. You might know that these are dual problems. There's this max flow min cut theorem that says the capacity or the amount of flow you can send from a certain value, from a certain node to another one, has the same value as the capacity of the minimum cut between these two nodes. The point is that flows usually have a source and a sink, so there are ST flows, and then we're considering ST cuts, so only cuts where S and T must be separated. Whereas in this problem, we are considering the global min cut. We're not really interested in what we cut away, we just want to destroy it in some sense. Okay, that makes the problem a bit more general, and the direct method would use a linear number of max flow calls, so that would be a bit expensive maybe. Yes?
I think you can always generalize a min cut to a ST min cut by just adding two nodes with edges to each node.
Well, and what happens if, so your suggestion was like for the max flow problems, it's often used as a reduction if you have multiple sources, multiple sinks, you add a super sink and super source and connect these. But you have to be careful that you don't just cut away that new node. So I'm not an expert on min-cut algorithms. Actually, I don't know if there's a very simple method. I don't think so. So for deterministic algorithms, it seems that the best algorithms have the following runtime. It's n times m for the vertices and edges as usual, and then log n squared over m. And if they're the same, then it's a cubic running time if you have dense graphs. Sorry, that was nonsense. In the worst case, if the graph is dense, then m can be n squared. M can be n squared. Then these two are cubic, and this is just there should be some +1, I guess. Okay, another question.
Regarding the problem definition, if we don't have an S and a T, then do we require that V1 and V2 are non-empty?
Yeah, we would like that, I guess.
For a certain size? Or
Yeah, so
just not empty?
yeah, just not empty. Otherwise it would be kind of boring. Yeah, but we really don't care if we just cut away one node. That's feasible. Okay, so for the sake of this lecture, we will just take for granted that the deterministic algorithms are either cubic and well, maybe even use max flows, which are not the very most efficient in practice. Well, they're extremely complicated. There's a few more sophisticated methods like this one, but they're complicated to implement. And again, there's a randomization argument that makes for a very simple algorithm. And in the first step, it will not do any good. But with a slightly clever trick, it will turn out to be an efficient algorithm. That's actually better than any deterministic ones that I know. And the simple primitive step, let me just draw a new example to make that, to include all corner cases. That's the notion of edge contraction. So the idea is we choose two nodes and then we contract that edge. We make a new node. Let's keep it blue. And then all the other edges are essentially still there. But if formally these were going to the two different nodes, then they're now to the same node. And that might lead to the case that two formally disjoint edges, so in the representation where we here represent multiple edges as a weight, that might lead to two edges falling together, and then we just add up the weights, the multiplicities. Okay? So this is a simple operation that's often used for all kinds of tricks on graphs. Why does that help with a min-cut? If we just continue contracting edges, at some point in time we will only have two nodes. And then we can simply take these two nodes and determine all edges between them as cut edges. And the two nodes, by tracing back the contraction, represented two non-empty sets. So that gives us some cut, not necessarily a minimum cut. But we can just do that randomly, and then we obtain a randomized algorithm that returns a cut. So just for the algorithm, it keeps track of the sets that correspond to the vertices. Initially, every vertex is just labeled by itself, and then we keep on contracting in this simple version. We choose a random edge from all those that are still available, and we contract the graph. I left out the implementation details in that case. If you just take some adjacency list representation, it's easy to do something that's linear in the graph size. That's easy to do. You will probably consider this problem in the exercises again, because there's a much nicer and more clever way to implement this whole thing that's also much more efficient. But for the analysis here, it doesn't really matter too much what the running time of this step is. For the correctness, at least it's not important. Then for the new node that we created here, we set the label as the union of these two. We keep going until we only have the two nodes. And then we return the labels of the nodes. That's just the two sets that form the cut. And we can also give the cost, because that's the weight of this single edge that's left in the representation. Okay, so this is it's a simple algorithm. It runs in poly time. Okay, brave statement. But the probability to have the minimum cut is actually tiny. And it's going to 0 even quickly with n. So we will have to do something about this. But still, it's instructive to first prove this, because it's not even clear that we can at all bound this probability, maybe. Okay, a bit of notation that could fit here. If that's the original graph, we write g/xy for the graph that results from contracting this edge. So that's maybe the nicer way would be to simply use that notation here. And we will extend that notation just for a set of edges or a sequence of edges to mean that we contract the edges one after another. Well, it's obvious that the algorithm computes a valid cut, a feasible solution, because every node in the graph at any point in time corresponds to exactly the subset of original nodes that's in his label. And when we have reduced that to two subsets, then these are a cut. They are disjoint, they're not empty, that's by definition. What's unclear is the quality of the solution. It's also clear that we always do n-2 contractions. Let me add that we assume always here that G is connected. I mean, if G is not connected, the cut is pretty simple, right? Just cut two components, that's always the best you can do. So we assume that that's part of the pre-processing, run one depth first search, and if it's not connected, then you know what to do. And if it's connected, we always do n-2 contractions until we have this, until we leave the while loop. So we can certainly implement the whole thing in quadratic running time if we do nothing fancy, but just the contraction is just done by well, going through adjacency lists and replacing nodes by new nodes, adapting edges. And that means you always have, okay, yeah, okay. You have to be a tiny bit careful because this is n and not m. But you'll look at that in the exercise classes in more detail. Now the interesting part is when the optimal solution will be returned. And the important observation is whatever is returned is optimal if and only if no edge of the min cut was contracted. One direction is easy. If we ever contract one of the min cut edges, then we put two nodes that should have been in two parts of the cut into the same set, so we will never come back from that. And the other direction, if exactly the min cut edges are left, we never contract these, then, well, if we go on until we only have two nodes, then this must be a cut, then we have found the min cut, or one min cut. Yes?
The problem with the statement is that if we have multiple optimal min cuts, then the if and only if is a bit questionable. If there's only one solution, that's true, but if there's multiples, then...
Well, if there's multiple, if there's more than one optimal solution, you can read it. You first choose one of those, and then you return this one, exactly if you don't contract any edge from this specific one. Okay, it's a bit tedious to make it formal. You should first quantify over the solutions. In the worst case, you can assume there's only one min cut. As before, this is like for the satisfying assignment, it only makes the probability larger to succeed if there's more than one. Shall we leave it like that, or?
You could just write that we're assuming the worst case and there's only one solution. I guess that's what we're doing.
Okay, let's say C is optimal. Well, you know what? This is actually true for any cut. So if C is some cut, then we'll return C exactly when we don't contract any of the edges in this specific cut. And that in particular applies for the one min cut, and that's all we're going to use. So let's fix one minimal cut. And with respect to this one, we define events. Where the ith event says that the ith contraction does not use an edge from C. So these are kind of the good states. And we have these from 1 up to n minus 2 because that's the number of contractions. And then if we take all these together, that means exactly that C is returned. And that implies that we found an optimal solution, even though it might not be the only way to get one. Now the point is that these events are not quite independent because the probabilities change. If you know that the first so and so many events already hold true, that means there's still all of the edges in C left over. But if you have contracted a few edges in C, well, then you're already in a bad shape, but then the probability becomes larger to not take another one. So they're not independent. So we can simply multiply their probabilities. Nevertheless, we can quite easily compute the probability here by using conditional probabilities and iteratively using that. So I'll write it down. The probability to have all of these events I can split off the first one. And then for the second one, I condition on having the first one. Because if I have all of them, the probability, I can just consider how the events occur over time. In this case, it's easy because they're essentially ordered in time. I first ask whether event 1 occurs. And if this in the end should be the case, all occur, then first E1 occurs. Then the probability that also E2 occurs is the conditional probability. And we just keep on doing this until for the last event we condition on all of the ones before. It might look like this doesn't help too much. But let's start with a simple case. What's the probability in the first step to not pick one of these edges? There we actually need an observation and a bit more space. Let's call k to be the number, so the cost of our optimal cut that we are just considering, which in this case it's just the number of edges, but we include multiple edges. Then we know that the graph must at least have n times k half edges, because every node must have degree at least k. Because if there was a single node with degree k minus 1 or smaller, we could just cut out that node and have a better cut, a smaller cut. Yes?
Do we want to pick each edge with the same probability, or do we want there to be like two nodes being picked at random and their connection being shrunk? Because it's kind of different because we have a
Yeah.
graph, so
I think the basic version of the algorithm just takes the edges as in the representation, so including multiple edges.
so if there's multiple edges between two nodes, then the
Right, you
probability
just
goes up that you're choosing.
ignore that there are multiple ones.
I mean, you could, but then it possibly changes. Probably.
Yeah, it definitely changes the game in a sense.
Questions in a good way or bad way?
I think it's actually helpful to take the weights into account, because contracting two nodes that are connected by thousands of edges, right? That's actually an indication that these should be in the same set. It might not make a difference for this part of the analysis as long as we are consistent with what size is. But it's a good question, because the algorithm is essentially not well defined. It doesn't specify very precisely what it's doing, right? So
Since we split off C, and it's not saying that we consider C, it kind of
right.
seems
So this reads like it's choosing from the edges, ignoring the weight.
in that case we should probably redefine K as not the number of edges, but the number of connected nodes.
I think the way we're using it here, let's assume we include proportional to the costs. So if if there's multiple edges between two nodes, there's a higher probability to contract them. Intuitively, it makes sense, and so the point is that the nodes are at this point also not very precise, but the costs. So to make this argument work, we actually have to include the parallel edges. We say here the k is the cost of the min cut, so that's including the parallel edges. And also here, this m has the meaning of number of edges including parallel edges. So let's write it down. Because what we are using here now is the probability to pick none of these edges in this min cut is just given by this, or 1 minus k over m. And since we have this bound here, we can simplify that to this, and then this step would probably, let's keep it like this. We're including the parallel edges for sampling. It's good that you stay awake. So that looks pretty promising. At least for the first edge, we have a pretty good probability to not hit one of the cuts by the simple observation that if a cut has a certain size, the graph must have a certain number of edges. The problem will be that the probabilities for the later events are a bit different. So let's now look at the graph that we get after the first I-1 contractions. So what's left is n minus I plus 1 vertices. So we're now considering the probability of the ith event, conditional on all the formers being true. And this means none of the contractions up to now, so all of the edges in Fi, that's just the set of edges that we contracted up to now. Must be empty, so none of the edges must be from the min cut. And in this new graph, we're actually never removing edges, we just contract nodes. But edges between the two are removed. So we had before, we only said that for the entire run of the algorithm, but actually we need that here also before. So we said if we didn't contract any of the edges, then we return this. Now we're looking at an intermediate graph where we contracted a few edges, but none of the ones in C. And we have to show that this cut then still is a minimum cut in this resulting graph. So under the condition that we haven't contracted any of these, the reason is by contracting nodes, we only make cuts impossible, but we don't allow new ones. And the value of all cuts that are still possible are the same as in the original graph. Is that clear? So we have nodes. And a few cuts are impossible because we essentially grouped a few nodes so that all cuts that separated nodes in the same components here are now impossible because the nodes have been contracted. But all edges between components are still retained, at least with respect to their multiplicity. So contracting removes possible cuts, but it never adds more, and it keeps the weight of all cuts that are still possible. Which is, I think, if you forget about really contracting the edges, but simply remembering them as components is almost a trivial statement. You always count in a cut which edges cross this, and if you draw it like this, where the blue parts are the contracted ones, then the original edges that cross the cut, no matter which nodes they actually connected, so all these edges are still present. They might not be different edges, but they are retained in terms of multiplicities. So in this case, that all these events up to now are true, which means we haven't used any of the good edges from C as contraction, then this cut that we have in mind is still an optimal cut for the intermediate graph. And since the value of C hasn't changed, we haven't modified C, the cost of C is still K. We have less vertices in the graph, so we can again lower bound the number of edges in G after we have contracted these edges. It must have at least K times n minus I plus 1/2 edges, because that's the number of vertices. That's the same argument as before. No node can have degree less than K, and that's the number of vertices, so it must have at least so many edges. So for the probability, this means, again, by the same argument, well, let's write mi for the number of edges in this graph. And ni, that's a good notation. And we have this minus K. That's the edges we are free to pick. And we divide by all. And we use again this bound. And we obtain something similar as before, only that now there's this additional summand minus I down here, which shows you that if I gets large or close to n, then the probability is actually going down a lot. But for the current statement, we were just computing how bad it is in the end. So that means we can multiply all these terms. These were the conditional probabilities that we had up here. Now, like for sums, you rewrite that. So the smallest value you have is 3, and the largest is n. And then you bring that on the same fraction. So you have an L down here, and here you have 1 minus 2, so that's L minus 2 divided by L. And that's almost like a telescoping thing, only that there are 2 left, right? So for the smallest term, you're left up here with a 1 and a 2. And for the largest term, you're left down here with an n and an n minus 1. Oops. And so that's what's remaining. And if you like, you can write it as n over n choose 2, just because it's nicer to write. But actually, this was the form in the statement. Okay. So we found that this algorithm does have a guaranteed probability to succeed, but it's actually very small. Well, because by the standard tricks, you know that if this is the probability to succeed, then 1 over this, so n choose 2 many repetitions and expectation give you an optimal cut. So the idea now for optimization problems, of course, is you return the best solution you've ever seen in all the repetitions. Before, we always had decision problems, and well, for SAT at least, and well, we just continued the repetitions until we found a satisfying assignment. Now here, we don't recognize the min cut just because of any probability that we're given. We don't have an easy certificate for the min cut here, but we just repeat the algorithm so many times and return the best cut that we've seen in these. And this is the expected number of repetitions you need so that at least one of those had the cut, the min cut, or the specific cut C that we had in mind. If you multiply that by 2, then you know that with probability 1/2, you have the min cut among those. And if you continue with a few more, then you can make the probability of failure as small as you like, but in any case, you need at least quadratic repetitions, right? Before you get a usable success probability. And if you combine that well, with the n squared implementation for a single step, you're better off using this deterministic algorithm, at least in big O terms. There's a slight chance to improve that, as I mentioned, but you would have to improve it down to constant or something, or less than linear to make it better than the deterministic one, and that's definitely not possible, because you have to look at the graph at least once. And just to finish off, before we consider the solution next time, let's look at the problem. We've seen that for the first contraction, the probability is actually quite good to not pick one of the bad edges. But as we keep going and as the graph becomes smaller and smaller, the probability to pick one of the edges from the cut actually grows, because at least in the sense when we condition of nothing has gone wrong up to now, all of the bad edges are still left, but the set of other edges must shrink. That's exactly what we're looking for. And so the way out will be to stop a bit before the probability becomes too small to still have a safe edge. And there's two different strategies how to deal with that. One that's pretty straightforward, and another one that's quite nice. So that's what we'll look at next time.